Section 15.7, triple integrals in cylindrical and spherical coordinates. So some learning goals: know how cylindrical and spherical coordinates work, be able to convert between them and rectangular coordinates, recognize when cylindrical and spherical coordinates will assist you in integration, and be able to set up and evaluate triple integrals in cylindrical and spherical coordinates. So what's going on in this section here for cylindrical and spherical coordinates is that these are going to, in some ways, be three-dimensional versions of polar coordinates. So let's just recall polar coordinates right here. How do we write points in polar coordinates? Well, this point right here, you call x comma y. We know how to do that. Or you can identify this in terms of r and theta, where r is the distance you are away from the origin. Theta is the angle that you're making with the positive x-axis here. And here are the formulas that allow you to convert between x and y and r and theta. So the question is how to go to 3 dimensions. And as it turns out, there's 2 different ways to go to kind of generalize this up to 3 dimensions. So one of them is going to be cylindrical coordinates, one of them is going to be spherical coordinates. So first I'm going to talk about cylindrical coordinates is the easier one. Spherical will feel a little bit less natural, but will prove to be very, very useful for us. So how do we go to 3 dimensions for cylindrical coordinates? The idea is going to be that we have x, y, and z. We're going to do polar coordinates. So we're going to convert x and y to polar coordinates. And then the z coordinate we're going to leave alone. Or another way of expressing this, so let me put, okay, here is a point x, y, and z. What we're going to do is that we're going to project the point to the xy plane, and then find theta. Theta is just going to be the polar angle in the xy plane, and then r is going to be the distance, that's a bad marker here, the distance from the origin to projection in the xy plane. And then for z, what do you do with z? You just leave z alone. So instead of going x, y, z, we go r, theta, and z. So cylindrical coordinates, leave z alone, take x and y, project this down to the xy plane, and convert x and y to r and theta. So our, conversions here is just going to be x is equal to r cosine theta, y is equal to r sine theta, z just stays put at z. Going in the other direction, r is equal to the square root of x squared plus y squared. Tangent theta is equal to y over x, and z is equal to z. So this is our first way of doing things. If you can understand polar coordinates, you basically automatically understand cylindrical coordinates. So for example, let's just convert here. If x, y, and z is -3 square root 3, -3, and 5, let's convert this to r theta and z here. Well, z is just z. Z is just 5. R is going to be square root of -3 square root 3 squared plus -3 squared. And this crunches out, crunch, crunch, crunch. You should end up with, according to my notes here, this should give you 6. Theta here, so tangent of theta is y over x, is -3 over -3 square root 3. So tangent theta is 1 over square root 3. So we might think that this is going to be theta is equal to pi over 6, but we need to be careful about with the quadrant that we're in. We are in the third quadrant down here, so it's not pi over 6, it's pi over 6 plus pi. Theta is 7 pi over 6. And then converting from r theta z to x, y, and z is just, again, doing polar coordinates. So again, if you can do polar coordinates, you can do cylindrical coordinates, and we'll see in a few videos from now how to integrate using cylindrical coordinates. If we have regions that are like cylinders, and we can write them in bounds on r, theta, and z, there's ways to do that. But before we get to integration, the next couple of videos we'll have to do with spherocorns, which is going to feel a little bit less natural than cylindrical coordinates, but are going to prove to be very, very, very useful.